Okay, so this example is on the extrusion process. So in this example, we have a pellet that has a 75 millimeter long and 25 millimeter in diameter, is to be extruded. Okay, and remember what the extrusion process is. And this type is going to be of the direct extrusion. You remember in direct extrusion, the pellet will be moving in the same direction of the ram that pushes through the die's opening. Okay, so the extrusion ratio given to us here is going to be equal to 4, and the extruded cross section is going to be round. Die angle is going to be equal to 90 degrees. The work metal has a strength coefficient of 415 megapascal and strain hardening of 0.18. Strain hardening exponent is 0.18. So this is a K, and that's the value for the N. Now use a Johnson formula with the A equal to 0.8 and the B equal to 1.5 to estimate the extrusion strain. After that, you need to determine the pressure applied to the end of the pellet as the ram is going to be moving forward. So once again, we're going to go through the analysis of the extrusion. Wait a second. Yep, I'll put everything in. So first we have the extrusion ratio is going to be reduction ratio and defined as the initial area over the final area. The initial area is going to be calculated by knowing the diameter of the pellet itself, DO. And the final diameter is the diameter of the exit from the die. Well, you remember that we know diameter of the pellet, so we can find this one. The Rx is given to us as 4, so we can find the value of the AF if required. Rx extrusion ratio, the AO is the cross-sectional area of the starting pellet, and the AF is the final cross-sectional area of the extruded section. And this equation can be applied for both direct and indirect extrusion. The true strain in the extrusion, given the ideal deformation, occurs when no friction and no redundant work. So the true strain is going to be equal to the ln of the initial area over the final area. If we consider that the area is 2 pi r squared, pi r squared, that means we can say that the ln is equal to the RO squared divided by the RF squared. Now, under the assumptions of the ideal deformation, that no friction and no redundant work, the pressure applied by the ram to compress the pellet through the die opening can be computed by the following equation. The P is going to be equal to average flow stress multiplied by the true strain, or is going to be equal to the average flow stress multiplied by the ln of the Rx. Now, this one is given. We just need to find the value of the average flow stress. And this can be found from the same equation we use in the rolling equation. So the y prime f is equal to the k multiplied by the mu up to power n divided by 1 plus n. Now, various methods to calculate the true strain and the ram pressure. For example, the Johnson empirical equation can be used, that the mu x is equal to the a plus b multiplied by the ln of the Rx. For the indirect extrusion, the value for the pressure is going to be equal to the y prime f multiplied by the mu x. So if we find the mu x, we find the y prime from the previous equation, we can find the pressure in the indirect extrusion. In that extrusion, the equation can be modified to be P is equal to y prime f multiplied by the mu x plus 2L divided by the dO. The ram force is going to be equal to the pressure multiplied by the initial area. The power is going to be equal to the force multiplied by the linear velocity of the ram. Let's go back to the question, and we have everything should be highlighted again. So the L is 75 millimeters, the diameter O is equal to 25 millimeters, and the Rx is equal to 4, and the extruded section is round. The die angle is 90 degrees. The strength coefficient is 415 megapascal. The strain hardening exponent N is equal to 0.18. 0.18, yep. The A is equal to 0.8 and the B is equal to 1.5. Now we can use these parameters to do our calculations. So we're going to examine the run pressure at the pellet length of the L equal to 75 millimeters, then the L of 50 millimeters, then the L of 25 millimeters, and then the L equal to 0, and compute the ideal true strain, extrusion strain using the formula of Johnson, and then the average flow stress. So the mu is equal to ln of the Rx. Here is going to be the ln of 4. And then we can find the answer. For the mu x is going to be equal to the ln of the Rx multiplied by the B of 1.5 plus the A value. Then we can calculate the value for the average flow stress. So let's start now. For the first one, ln of 4, and this will be 1.3863. For the second one, is going to be 0.8 plus 1.5 multiplied by the 1.3863. And this will give me the answer to be 2.8795. Finally, the YF, we know the value for the mu, the N and the K are given, so we can find that the average flow stress is going to be equal to 373 megapascal. Now we know the YF, and we know the mu X, and we know the L. So now we can apply that to calculate the pressure's value. So we start first by calculating the pressure. This is direct extrusion process, so this will be the equation. We can start at 75, 50, 25, and 0. Simply by substituting the values, the first one is going to be 3,312 megapascal. Definitely, we're going to have the L to be reduced, and the L is a parameter of the numerator in the equation. We can tell that the pressure value will be reduced. Contact area is going to be less, so the friction is going to be less. So the pressure second is going to be reduced to be 2,566 megapascal. At the L of 25 millimeters, we're going to have 1,820 megapascal. And finally, the P is going to be equal to 1,074 megapascal at the length of 0 millimeters. Now, in this question, we don't have the value for the velocity, but I can calculate the force for each stage by multiplying this pressure by the value of the area with 25 millimeter diameter. Then if I'm going to be given a velocity for the run, I can calculate the power for each stage. Okay, thank you very much for your listening, and we're going to move to the forging question.